Okay, so today I'm going to first do Huffman coding. I think some of you know now Huffman coding. What is Huffman coding? Is for use for data compression. By looking at the say any English text or whatever, you can look at the frequency of letters. You know how they occur, and based on that, you can make an encoding scheme. Okay. So, for example, if some letter is occurring too often, you assign a string of small length, right? And so on, right? So that you can optimize a bit. So I'll show you. I'm not going to give you any theory or as such. Of course, one can describe the algorithm. I focus on an example. Okay, how to construct a tree you have in Huffman coding for the encoding purpose. Okay, so I'll just take an example. After that, we are done with the trees. Of course, there are a few more things how to traverse the tree and so on. But I think I'm leaving it. There are more intense codes on these things. When you look at data structures or design analysis of algorithm codes, you will encounter more and more such things. But finally, I think I am going to give you one very beautiful application of discrete mathematics in cloud computing. So I'll give you that example so that you know some more flavor how things are working. Okay, so let me start with Huffman coding. So suppose we are giving symbols. We are having symbols A with frequency 0.08, A with frequency 0.08, B with frequency 0.110, C with frequency 0.12, D with frequency 0.15, okay, E with frequency 0.20, and F with frequency 0.35. I'm just taking an example of symbols. Suppose we have 1, 2, 3, 4, 5, 6 symbols, and with some frequency, right? How they occur. So I have to design an efficient coding scheme so that it is going to take less space. So the idea here is that I should assign uh, with whatever is having more frequency, I should assign less number of bits. Okay, so that is the key idea. So how do we do this? So I am going to form a tree. So this is known as forest, right? So it's a simple forest. We saying that some collection of objects are there right now. So I am going to form trees out of this, a final tree, which will give you the encoding procedure. Okay. So what I do, so I look at all of them. Which one have lowest frequency? You can see that 0.08 and 0.10. These two are the lowest frequency. So I'm going to combine them. Okay. So what I am going to do in the next thing, I'll just write C as it is, which is 0.12, right? And then D, which is next one, 0.15. And then I'm combining 0.08 and 0.1. So this is 0.18. And I'm making 3, B on the left, A is on the right side. Right side is the lowest frequency, left side is higher than that. And I'm assigning 0 here and 1 here. Okay. So like that. And then we have, which is 0.20, and F, which is 0.35. So what I have done from this initial step 1, what we are doing, we are looking at the lowest frequency and combining and forming a tree such that the sum of these frequencies is at the top, which is 0.18, and the lowest one is on A on this side, and the highest one is on this side, which is B. And then I'm assigning on this side, if symbol is assigned on this side, I'm assigning 0 here. On this side, I'm assigning 1 here, right? So I have formed a first tree, step 1, right? Okay. Now I am going to look at the rest of the things. Now we have 0.12, 0.15, 0.18, 0.20, and 0.35. Which one are the lowest? C, D are the lowest. So again, I can combine them, okay, and do the same procedure, right? So here it will be 0.27, and then I'll combine D and C here. This assign as 0, this assign as 1, And the next one is, of course, 0.35, which is F, right? And now E, so E is 0.20, and I can combine with 0.18. What is the value? 0.38. So that can come here somewhere. 0.38, and this E will come here. This one, 3A, 0, 0, 1. Okay. This is the next step. So basically, C and D combined, so we'll give you 0.27. F is the next one, which is the highest one, 0.35. And then we are combining, so this E I am also combining with A and B, basically, right? So I am forming the next step. You can see that this 0.18 and 0.20 is 0.38, which is here. And then we are forming in the same manner, right? So next step, right? So we are forming the tree. Now, from this step 3, I can again, so now there are 3 trees basically, right? One is with 0.27, another one is 0.35, another one is 0.38. What do you think could be the next step here now? 0.38, when we combine, so basically 0.27, 0.35 is the lowest one, right? So I can combine them again, right? So basically, if I combine these two, left with here something, 0.38 is E, 0, 1, 0, 1, EA, and this 0.62, the other two I am combining, F on this side, 0, 1, B, C. This is step 4. So we are left with these 2 trees. Forget about this line, actually, it's just like that. So now we are left with one tree. The value is 0.38, other tree 0.62, right? So I am going to combine these two also. And that left-right business, I am keeping track how we are putting, right? So final one will be 1.00, 01, okay, 01, D, C, 0, 1, E, 0, 1, B, A, 0, 1. This is our final tree when we combined everything. These lines are coming, but forget about these lines. So this is 0, 1. Okay. So D, C, B, A, E. What else is left here? This is F, right? So basically now I can read what is the encoding for A. Encoding for A is what? 1, 1, 1, 1, right? So 1, 1, 1. Encoding for B is 1, 1, 0. Encoding for C is 0, 1, 1. Encoding for D is 0, 1, 0. Encoding for E is 1, 0. And encoding for F is 0, 0. So we are able to find these encodings for the letters. Okay. And you see now you can clearly check that the frequency which is the lowest is coming with a less number of bits. So one can ask how many total bits now we require to represent the whole tree. I mean, I can compute. So this will be something like, so 3 bits for A, 3 bits for B, 3 bits for C, 3 bits for D, 2 bits for E and F. So average number of bits will be 3 into 0.08 plus 3 into 0.10, 3 into 0.12 plus 3 into 0.15 plus 2 into 0.20 plus 2 into 0.35. So this turns out to be 2.45 bits, right? So clearly you can see that how many bits, how many symbols were there? 1, 2, 3, 4, 5, 6, right? So maximum is 3 bits, right? If you assign 3 bits all, it will take more bits, right? But now we are taking less bits. So of course there will be data compression. It's a beautiful algorithm actually, that was discovered by Huffman. This is the binary. For the binary ones I have shown you, of course, there is ternary or higher things are available. I think some of your students have already know the higher one, right? They've implemented it in your class as a project work actually. Anyway, so that's something all about Huffman coding. Uh, now I am going to show you. Okay. Now I'm going to now show you cloud. Okay. So cloud computing. So most of you access Gmail, right? Every day. All of you have a Gmail account. So have you? I mean, do you wonder how it works actually at the back end? How your data is stored, or Google is replicating data packets how many number of times? It's a very beautiful question. I mean, you can search. I think at one point of time, I remember when I paid these stocks. This stock is quite old though, but at that point of time, it was 35 times. Each packet was replicated 35 times across different servers. Okay, so and you want to access the data. Okay, here I will show you a beautiful technique that was discovered by Demarcus in year 2007, and the idea is, in the current scenario, whenever we are storing data in the cloud, whether you use Facebook or Amazon services or whatever, or iCloud or whatever, so normally your data is decomposed into chunks, and those chunks of packets are replicated certain number of times across different servers, right? Okay, different servers across the globe also. So now whenever you are accessing your data, actually, right, so these packets are combined and the file is produced. So what happens? So this is something is fine. One can do this technique as engineers. You don't care about efficiency, and many times, just replicate. It's a common sense. If data fails, you can recover it from some other. So one packet, one server is down, you can get the same packet from some other server. Of course, there will be a file system which will manage everything, right? So that is something easy. But then it is a wastage of resources. And Demarcus et al., he was at University of Southern California at that point of time. Now at University of Texas, I guess. Yeah. So he discovered that you can devise a beautiful mechanism using mathematics. What you do, you take the file, decompose into certain packets, encode them, and throw in the cloud of n servers. Now you contact any k nodes in the system, any k nodes, and you can recover the file. Beautiful property, mathematical property. Okay, it's not, so basically now packets are not just merely replicated, but in a smart manner things are done so that you contact any k nodes in the system and you will be able to recover the file. Okay, and if node fails, because node failure is a very common thing, something may happen, server is down, light is not there, whatever, anything may happen. If a node fails, then the data in that node can be repaired. There are two ways of repair mechanism. One is whatever was lost, you replace with the exact that data, or it's a functional repair. Functional repair means that property that you contact any k nodes and you will be able to reconstruct the file will remain true, no matter which node is failed. So if a node is failed, you can contact any d nodes in the system to repair the data. It's a beautiful property. You see, the first property, that the file can be reconstructed by contacting any k nodes in the system. And the second property, if the node fails, you can contact any d nodes in the system to repair. Okay. So I'll show you how this beautiful concept, came around in 2007. And, now I think after that, many companies like Facebook started moving towards this. Microsoft Avalanche file system is based on this technique now. So all these new things now people are, become commercial. Once the technology is there, beautiful things are there, and that beautiful things can be done from this. Let me show you. So I'm going to talk about dress codes. One sunny morning you woke up, Gmail is down. But how many times you saw that Gmail is down? I think I have some small captions, but probably you might have seen recently also. I'll show you the picture actually when it was down. So actually, Gmail is a service provided from Google Cloud, right? So it's a cloud computing. The idea was by John McCarthy, that computing should be delivered as a public utility, like roads, internet, right? So computing should be also given as this kind of service. And so normally the data is stored is in cloud data storage, and there are key issues like cloud reliability and security. Two are very, very important things in terms of cloud computing. And of course, you can talk about unlimited services. I mean, you are familiar with Amazon services, right? AWS and so on and so forth. So many services are there based on cloud. Some cloud services, Amazon S3, which was started in 2002, Koala, Dropbox, all these things Amazon Elastic Compute started in 2006, Google Apps 2009, iCloud 2011. So this talk was, I mean, it's quite old talk where I gave, and these things were happening at that point of time. And there was a commission on the leadership opportunity in the US deployment of the cloud in July 2011. The US government, everything is done from the US government only, right? So they dictate the technology actually. So now you see, there are some. This is the news in 2009 Gmail outage. You see, the Gmail was not working. And there was, another news in 2011, Amazon trouble raises cloud computing doubts. People say, okay, well, cloud computing will work or no. It's working because of mathematics, right? Backend mathematics, which is supporting everything that now, you know, uh, it's working. So anyway, so there are news of Gmail outage in 2009. I think you were born in 2009, right? Anyway, so I don't remember. So this is a cloud data center, IBM cloud data center in Auckland, New Zealand. There's another one in South Korea. But this cloud is unreliable. So data is stored in a distributed fashion. So what is known as distributed storage system, DSS. Okay, and why it is unreliable? There may be hard disk failures, network failure, right? Peer sharing or malicious node. Somebody is trying to tamper the node, right? Some node there is a problem. So actually, coding theory is there for rescue. Of course, you may say that I am a little bit biased because coding theory is my area of research. But anyway, so how to control errors in any kind of scenario. So in cloud computing also. In fact, in this work, I am going to show you some of our work done by two BTech students here in the class. They have done this actually, by the way. And, so anyway, so let me show you how it works. So coding theory started, of course, there were earlier codes were known in India also as a binary form, and there are a lot of history. I'm sure, I mean, you can find some of my other lectures on YouTube on coding theory, but I'm just mentioning the Richard W. Hamming. Richard W. Hamming in 1947, so he was working at Bell Labs, and he was working on Model 5 Bell Laboratories General Purpose Relay Calculator. He was solving differential equations actually, for all these Manhattan atom bomb projects and so on and so forth, right? So he used to give calculations to the computer of that time, and he used to give it on Friday. Weekend is off, and Monday morning he comes. Computer has made an error, and so it stops completely, right? So then he asked, after frustration, when a computer can detect an error, why can't it fix and correct it? And that gave the birth of error correction or error control codes. It is because of error control codes you see your RAM, VLSI, everywhere error correction is a very, very fundamental thing, or your network communication, wireless communication, satellite communication, deep space communication. Whenever you are doing any kind of communication, video call, video chat, anything, or you are storing data on any kind of disk, hard disk, cloud storage, which I'm going to show one application, or even DNA storage, right, or whatever. So error correction is very, very important thing. So that was the invention is credited to Richard W. Hamming. Of course, the Hamming code that he discovered for correcting single errors. By the way, you are lucky that you can get his own lectures. Hamming has given lectures. Those are available on YouTube. You can watch while he's teaching. I mean, of course, he also have a stomach. You can watch. When anyway, so it's a nice thing. So he gave this idea about error correction, how to correct single errors. So coding theory is everywhere, right? Any information processing device either sends data from here to there, communication, or sends data from now to then, storage, right? So redundancy is a very basic error correction mechanism. So whenever we are speaking to each other, and if you're not able to hear, then you will say, please repeat. So repetition is a crude form of error correction. So every time we use, error control is everywhere in engineering. In the entire engineering domain, no matter which area you go, whether VLSI, robotics, IoT, or whatever, error control is very, very important. Whenever you're making any engineering device or whatever. And so it has plenty of applications, as I mentioned: data transmission, data storage, digital audio, video transmission, space satellite communication, mobile communication. And of course, I have written a paper in biology, the quest for error correction in biology. You can look at it. In biology also, most of the biological process, error correction is by default there, right from your brain to many other parts of the body. Chemistry, chemical reactions are also very, very important. And of course, cloud computing. So I'm going to talk about cloud computing now. So how do we construct basically these codes? It requires some combinatorial mathematics or discrete mathematics, that you say, algebra, algorithms, and of course, depending on the application that you are using, right? By the way, this is interesting quote: an ounce of algebra is worth of a ton of verbal arguments. The people are fighting, just give them 1 ounce of algebra and it will be settled, right? Whatever they're doing. So here is a Google file system. There is an app. There is a master server. Okay. And so there are chunk mappings, chunk servers, and then so it's a file 1, chunk 1 on chunk server, that chunk server. It is also replicated on another chunk server, file 1, chunk 2, file 1, chunk 2 here. So redundancy is there inbuilt into the system, right? That is how Google file system works actually. So as I mentioned, at some point of time, it was 35 times replication. I'm not sure what is the current thing, what they are using, but because these things keep on changing, but at one point of time, it was 35 times, packet was replicated. So the question is, I mean, this is kind of wastage basically, right? Because you're just simply distributing, right? Packets replications. It's not very efficient way of doing the things. And by the way, so if master fails, everything will stop. So master is also, shadow masters are there. If this fails, next will take care of everything. If that fails, next one will take care of. So there, this is also replicated, and everything else is also replicated, right? So that is how Google file system works. Now look at this very beautiful scenario. Suppose you have 2 MB file, 2 packets, 1 MB each, A and B. Okay. Now there are there 4 nodes. Suppose I'm going to describe 2 mechanisms of providing storage, how it works. In one way, I mean, one way what we are doing, this 2 MB file, there are 4 nodes. I am replicating each packet twice. So node 1, packet A, node 2, packet A, node 3, packet B, node 4, packet B. Okay. If I do this replication, what happens? If suppose this node fails, node 2 fails, I can recover data from node 1. No problem, right? So this is how, very simple way, simple replication. Okay. It's not a very efficient one, but bandwidth wise, it is very good actually, because you have to just download the data. There is no computation involved, right? You just simply download the data. And this input output is also very fast, okay, for this scheme, okay. And you have to download only 1 MB data to repair. Now, this is another scenario. This is known as eraser code. I take 2 packets. So A is here in node 1, node 2, packet B, node 3, sum of the packets. Okay, and this is A plus 2B of the packets. So we are taking linear combination of the packets. Remember, packets are elements of the finite fields, right? So you know that why they are important. So now if a node fails, if a single node fails, I can recover anyway. right? If 2 nodes fail, then also I can recover by solving the equations, right? So this is providing reliability better because it tolerates 2 failures. This scheme tolerates 1 failure. This scheme tolerates 2 failures. But of course, the computational overhead is there in this case, right? The question is, can you provide much better method? How do we provide a much better method which can increase the tolerance in terms of failures and it can minimize the bandwidth, right, in repair, and disk input output should be fast. What is the best scheme that is possible? Okay, now in fact, Demarcus has shown that you can construct error control codes which are of two kinds, MSR, MBR. So minimum bandwidth regeneration or minimum storage, right? So you can minimize the bandwidth or storage. You should not also replicate. If you store too much information and too many, so storage minimization is also important thing, right? So in fact, he has shown that the repair bandwidth can be reduced further by using random linear network coding. I mean, at least you know there is something random linear network coding. If each node is willing to store more. So how it works? There is a file. These symbols are there. I mean, this is basically known as regenerating codes. A codes which will regenerate the data. The regeneration mechanism is of two kinds: functional versus exact. I mentioned to you what do you mean by exact. Whenever data is lost at a server, you are replicating with the exact data loss. Whatever was lost, you have to produce the same data. Other one is functional, means that property that you contact any k nodes and you should be able to reconstruct the file remains true. Okay, that should be the key thing. So this is the repair type. So if you have n nodes in the system, each node stores alpha symbols. So data can be collected by connecting to any k nodes, right? I mentioned to you. Now I can show you a small. You see, this is a data collector. These are say n nodes. If you want to data reconstruction in generating code, you contact any k nodes in the system and reconstruct the file. Okay, any k nodes. And if you want to repair, if a node fails, you can contact any d nodes in the system and download beta packets from each. So repair bandwidth is d beta, right? And so you can repair the a node. These two mechanisms are important in regenerating code, which is repair mechanism and file reconstruction. So it is a multi-dimensional optimization problem. You want to provide reliability, want to tolerate as many failures as possible. You want to minimize the storage. The storage on each server should not be too much, should be minimal. Bandwidth should be minimum whenever you are repairing anything. This input output should be fast, right? Should be fast. And scalability. आज 1000 यूजर है, कल 5 लाख यूजर हो जाए, 10 billion users, still it is working fine, right? So the scalability should be there. So these are the things when as a cloud engineer you are thinking about how to provide reliability, and of course security is also one of them which you can add. And I think you know that now in cloud security, FHE, fully homomorphic encryption, is a very important technique. I think some people are working with me on that, but anyway, that's something interesting. So the question is, can we have exact repair codes with minimum overheads of repair bandwidth, discretes, and computations? The answer is yes. You can use what is known as dress codes. Let me show you what are the dress codes. So dress code stands for distributed replication based exact simple storage. Dress codes, right? Something fancy always we use the name used by Kannan Ramchandran. I think last time I met him in 2018. So what happens? There are 14 packets. We use a code known as MDS code, known as maximum distance separable code, but don't go into the details. But these 14 packets, we add one extra packet, 15 packet, which is simply a sum of all the packets. Suppose, okay, just a paired check, okay, And then you distribute among these 6 nodes in this smart manner. So question is, how do you find that this kind of smart distribution is possible among the nodes? I'll show you why this is important and how to construct these things. So let us take this small example. User has 6 MB, I mean you have 6 MB file, 6 packets are there, 1 MB each. Last packet is added, which is a parity check of all the 6 packets. Okay, okay. So now we have 7 packets. How many nodes are there? 7 nodes. And we are distributing them in a smart manner, such that you contact any 3 nodes here. Contact any 3 nodes here, you will get all the packets. Say, for example, if I contact node number 2, 3, and 4, so what I am going to get? 1, 3, 4, 5, 6, 7. Which packet is missing? 2. But which is just sum of the all other packets, right? That property remains true among the packets, right? So we can get all the packets. This property is true if you contact any 3 nodes in the system. You can construct the whole file, right? Correct? Any question? Right. Now, I have a question. So one more thing now, you can note that each packet is replicated 3 times here. Replication factor is 3. 1 is replicated 3 times, 2 is replicated 3 times, everything. It's a beautiful thing, right? Beautiful rearrangement. By the way, in the first class, I asked you one question, T-time problem, if you remember. You remember? So you may ask, how do you know this solution? Class 1, if you recall, I asked you this question. There are 7 points, 7 lines. Each line contains 3 points, and through each point, 3 lines are passing. Remember? Exactly that configuration is giving you this beautiful pattern here. Solving the engineering problem. You see the beautiful mathematics? So let me show you how it works anyway. Okay, so one thing is that, so if there are node failures, you can see that it can tolerate up to 2 simultaneous failures, right? Even if 2 nodes are fails, you can reconstruct the whole thing. Okay, so for example, if node 1 fails, so you will contact node number 3, 3, 5, and 6 to construct the node 1, right? Whatever data packets were lost there. It's a table-based repair, beautiful thing. Minimize repair bandwidth because you're just simply downloading, you're not doing any computations. Minimizes disk input-output calls also. Okay, uncoded repair, no processing of data. I showed you one example where the linear combination of the packets were restored, right? This is not needed here. And if 3 nodes fails, download the complete file and reconstruct the lost data, right? One thing is there, here, repair is not flexible with respect to who can help. I told you one property that regenerating codes, what Demarcus gave, the idea that if a node fails, you can connect any D nodes to reconstruct the file. Here, that property is lost. That instead of that, you contact some nodes, some specific nodes to reconstruct the file. That is the difference. Okay, so I think that is clear. The question is, how do we construct? So basically, if you do simple replication, suppose 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 7, 7, 7. Is it going to work? No, because if user contacts any 3 nodes and you are getting only 3 packets, 1, 2, 3, not everything. So there is a problem. So you require a smart replication. Okay? Smart replication. This guy here, see, you remember this picture? 7.7 lines, each line containing 3 points, and through each point, now you see that lines corresponds to storage node. So for example, node 1 has packet 1, 2, 3. This node has packet 3, 4, 5, and so on, right? The whole configuration. See the beauty of mathematics, right? It is solving the engineering problem, right? In the cloud computing, right? So there is a theorem, of course, by Kannan Ramchandran. This kind of thing is known as Fano plane or projective plane of order 2. A projective plane of order m gives just codes with total number of nodes this much, and replication factor is m plus 1. Okay. That is the theorem. Of course, you don't have to go into the details of the theorem, but at least I hope you got the idea. Now, the question is, can you go beyond this configuration? So when this came actually in 2010, immediately we thought, can we do something? Because ultimately we have to use some discrete math. Now you see, Kannan Ramchandran gave another idea. So in fact, they also use what is known as standard triple system. This is also another discrete mathematics construct. I'm not going into details of it, but at least I'll show that that is also that. So this Fano plane is a special case of standard triple system. So basically, that also gives you solution using lines as nodes and points as packets, for constructing dress codes. Okay, and then there was an open problem in 2011. Can we go beyond standard triple system and construct dress codes? So it was an open problem in 2010. Then two of my BTech students actually, they said that probably they can solve it. And then we did something beautiful. I'll show you that. So Kannan Ramchandran actually gave this idea. If you use regular graph, some time ago I told you about regular graph, right? You see that if you take this regular graph, you can get this configuration. Okay. So what sees as node and edges are packets, So for example, if you look at node 4, packets are 3, 4, 11, 10, right? 13, yes. Right? Edges पे आपने numbering कर दिया, right? Edges are numbered. So from a regular graph, I can construct this smart replication of packets, right? So regular graph. Can we do anything better? So we know that if there is a regular graph, we have the solution. That was actually done by Kannan Ramchandran and Salim. And so in fact, I'll show you our contribution. Look at this. We came up with this idea of partial regular graph. It's not complete regular graph. So each other vertex has same degree. For example, this is degree how much? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Each vertex is 7 degree except U9. U9 is 1, 2, 3, 4, 5, 6. Degree 6 only. U9 has only 6 packet. One is null packet. I mean, you are only using 6 packet. So this kind of construction also provided a solution. Okay. So this was done by these BTech students, as I was telling, Anupam Agarwal and one more person was there. So so this is a beautiful solution, and I think they have connection with circulant matrix. Circulant matrix, I'm not going to discuss. I mean, this paper is there. If you want to read, you can read it. This is the way you construct it using permutations and circulant matrix, and finally, then we have done a lot more constructions after that. But I think that's all. So all these are partial regular graph. Okay. So that's all. So I hope you got some idea about how discrete math is used in cloud computing, the recent application. And now I think many companies are moving, like Facebook and other companies are moving towards these solutions to implement, to build systems which are reliable and efficient. Okay. So I think that's all for the course. Thanks a lot. I think, I hope I have not bored you a lot over these 21 lectures, but my objective was to ignite interest in you for mathematics, see the power and beauty of mathematics, that you can build any technology. If some of you can start a company, technology-based company, based on discrete mathematics or whatever, any concept of mathematics, that will be a great thing, right? So if you need any help, startup funding, I'm also available for that. I can provide you funding and all those things, right? I think that's all. And I think the exam point of view, you have only 4 questions in the final exam. So as I mentioned, if you are able to do all 4 questions correctly, you will get AA grade, right? Or if you do extraordinary work in project, then also you get AA grade, irrespective of your performance. So another testing thing to do, right? Any questions you have from your side? No questions? So good luck. So see you sometime soon in next class. ठीक है, अब क्या क्विज करना है? I think that's all, right? Okay, thank you very much.